Let's see if it works.
Amazing, yeah.
Okay, cool. So, yeah, it's always hard to be the second presenter after a good talk, so I'll try to stand up for it. So, first of all, thank you for having me here. So, my name is Noam Shaish, so I'll start by presenting myself because I guess Adam is not his first time talking here. I'm still new to Scala in the City. It's my first time, so a bit about myself. So my name is Noam Shaish. I'm a father of two, so I have a daughter and a son. And second of all, I'm a software engineer for the last 10 years. So working from mainly started from Java and pretty quickly after that moved to Scala, as you can see. I'm coming from a different, for me, it's always seemed like from a different community of the Scala developers whenever I see ZIO and those concurrent development in Scala, because I'm a big data engineer. So the set of technologies is a bit different than a lot of times. So yeah, it's interesting. I hope I'll manage to interest also the people on the call here. So yeah, so BMW autonomous driving department, that sometimes it's bring up a question, okay, why big data? I mean, wait a second, use image processing in autonomous driving. We're expecting something which needs concurrency, is pretty intensive and so on. And big data is not something that runs in the car, right? So why do you need big data in the car? So that's one thing that I will try to explain here. And regarding the monad transformers, which I guess monad transformer and type classes that I guess most of you are more interested in actually understanding. Well, I assume, yeah. Well, so what I'll try to show is a use case. So a lot of times, what I've when you look into monads and monad transformers and type class and so on, you get pretty much artificial examples. And I would like to show a real use case of how we've used it in order to really in a production environment in a very high scale, and how did it help us basically to achieve some requirement that we had in a specific part of what we are doing. Okay, so why do you actually, so I mean, this talk won't be as hands-on as Adam's talks, and I'll have first part will be presentation, and afterward I'll show code and go through the code. I hope you'll enjoy it. So why do you need big data in autonomous driving? So I mean, I've been trying to find how I can sum it up in really one sentence to try and to explain it. So if you think of the car as kind of the brain, so basically autonomous driving is all about the brain of who drives the car around. So in order to get the brain working properly, you need to have a really good gym to train it in. And that's basically where the big data comes in it. So first of all, the cars themselves, they are packed with different sensors. So from cameras, which I'll expand, there are LiDARs, there's different types of sensors all over the car that basically produce a lot of signals. So in terms of frequencies and also the variety. So you have different sensor, different producer, all this different type of information that's running on the different buses needs to, in the end, play to play into one decision of, okay, should I slow down? Should I go faster now? Should I change a lane? Should I stay on lane? So there's a lot of data that the car themselves produce while they run. And beyond that, in order to prove that the car is good enough to drive on the street, what we need is we need to have a lot of kilometers that were driven. So millions and billions of kilometers that are actually being driven, and that's usually not enough just to take a car and drive around, because you don't only want to have a lot of kilometers, you're also interested that the kilometers you've driven are there are some interesting scenarios that are happening in them. It's not just enough to have, okay, I drove this road a million times over and over again. That's just not going to make it, right? There is, while driving on the road, even on highway, there's so many many different scenarios. It's enough that there was a bit of rain, or there's a sun which is in front of your face, or you had a curvature of this angle, you were driving this fast or that fast. So there's many different scenarios that you want to validate that whatever your car is doing correctly. Okay, so in order to do that, we also need to be able to simulate those scenarios and to kind of reprocess this software that basically we developed for the car. And so all these things need to happen in our data centers. And what is, and again, another interesting part of it, that while we are having fleet of development cars, a lot of the scenarios we just won't meet, right? So it's just not possible that with some, even if you have hundreds of development cars driving around, you won't get to all the available scenarios. So this is where we also have, we need to correlate and the data and information that come from the customer cars, the ones that consent for us to collect some information on them, right? So coming to this conference, I had a bit of kind of, it was hard for me to decide, yeah, do I want to go through it? Because I guess my feeling here that there's probably a lot of functional savvies. And coming from the big data domain and working with Spark, at least in my perspective, you are kind of limited with how much functional programming you can do in it when you're working in such a framework, which basically give you most of the abstractions you need, and the only thing you will need is just write functions. So you can be functional just by writing your own functions and just running them through so I hope I'll stand to the to the standard of functional programming that is here. Okay, so maybe a bit of how does it actually, what is actually happening in the big data world or in the autonomous driving. So first of all, like I said, we have a fleet of development cars. So those cars, these are cars that pack with, some of them packed with even more sensor that we'll have in a normal car, because we want to have more information from the development drives. And that's happening in multiple multiple countries. Yeah, so it's an international logistic thing that we have cars driving in the USA. Then we want to also to train the cars to drive in different in USA, in Europe, and also in China. So we have a lot of cars driving around the world. And after this data is arriving to our data centers, we need to basically ingest it. So the cars themselves, they produce a lot of data, which is being recorded, but they need to somehow also being ingested and processed to something useful later on down the road. So if it's for labeling, so labeling means, okay, we need to also see what happened in it. So not everything we can recognize, so we need even manually labeling sometimes. And then there's coming more analytics and machine learning on top of it. So a lot of post-processing and more kind of trying to understand what happened in the different drive and how can we leverage it to improve. And so this is some things, and all of that comes around the actual development of the software in the car. So software in the car, you'll have probably embedded the software, which is people which write. They are very good in writing efficient code and stuff like this, but they are probably not big data developers. So they can write very good online algorithms, but when it comes to, okay, how do I process petabyte of data? That's not their domain. So it's also something that we need to take care of. So saying that, I'm going to focus now on one of the types of data that we have, and this is mainly cameras, so mainly images. So what is so interesting about images? So first of all, is we have a lot of cameras in the cars themselves. So cars are just packed with images, because image processing and visual recognition is really important for autonomous driving. Okay, so what I'll show now is there is many setups of the car. So I mean, this is why the picture is very general, and those images themselves, they are very, in terms of data-wise, most of them are big data by themselves. So even each data point can be pretty big, and they come in a big scale. So there's a lot of them, a lot of cameras running, as I said, and the frequency is pretty high with high resolution in order to be able to basically identify more and more things on the fly. So just to give a bit of understanding, when I say big data and I say a lot of data, what do I actually mean? So if we have on the hundreds of development cars across the world, we have each car can produce up to 8 terabyte per hour for a drive, and we have approximately 2 petabytes or more. It can be at busy days can be even more of data that is being ingested daily into our data centers. And all this data, out of this data, a big chunk of it is just the images, because it's just a lot of data that is being produced from those images. So, okay, so what's the problem? What is your problem with images, and why do you keep seeing it, and what you basically what do you want from us? So the main problem with the data that arrives, that there is a very long chain of producing the data. So first of all, there are sensor manufacturers, the people who actually generated created the cameras, and they have their own, they have a very demanding requirement in terms of bandwidth and speed, and also what they need to do. So they have their own protocols, their own way to compress, and their own way to handle the images. And then there is some sensor integrator that will take this. They might have another physical component in the car that might take this data coming out of these images coming out of the cameras, and will do some translation so the rest of the car will understand it. So in addition to that, you will usually have some steering internal team that kind of need to explain this to the rest of the development area, and also they also sometimes need to try different things. So they can flash different versions. They will change things on the fly to basically verify what they are what they need to communicate and what they are handling with. And after that, you have the actual function developer, the guys that actually writing code that runs in the car. So they also have a say in, okay, what do we actually need from you guys to produce? So they also might have their own cars. So there's some teams have their own dedicated cars only for their development, and they might flash it and set it up differently and to have different variety of the setup. And in the end, there's also the car fleet engineers. So people who actually goes into the car and connect the different cameras or sensors or different setups and buses, and they all do this. I mean, for me, it's always looked like magic how they manage to make it happen in the end. But they knows all what needs to go where and how to connect it in order that everything will play along nicely. And when we come to the data center, so we are not in all this magic. So all this kind of symphony is happening in the car on the fly. But in the end, you have some logging infrastructure that take all this data that runs around the different buses and kind of log it into some disks. And they have their own requirements. So they have their own formats. They have their own way to compress the data. So each party of this in this chain might have different changes to the actual. They will have their own specification. They will have their own way to their own requirement, their own protocol that they're using. So in the end, we need to kind of figure out, okay, how do we handle the data? How do we process it that later on you can run just normally some kind of analysis tool on top of that. In addition to it, so you will have multiple cars, as I say, and each one of them have different setups. So when the data comes in, you cannot really be sure how the car looked like when it was running. So the same car might be once with 4 cameras, then 12 cameras, this changes. So there's different variation of the cars themselves. Adding to it, there is different schemas, color schemas. Some might be YUV, some might be RGB. There's all a matter of setting up the different sensors in the car when you're running it. Adding to a different resolution. Some cameras might decide even to change resolution between the different frames while they are coming, because it's just for compression wise. So, okay, you want high resolution, but I cannot give it for you for all frames. So I'll give you X frames in a very high resolution. They'll have a sudden drop of the resolution and jumping up back and again, and just to reduce them to stand in the required bandwidth. talking about is also frame rates, right? So you could set up the cameras to have a very high frame rate or lower frame rate, and there is also different variation of the bits per pixel that you actually gonna get. So you are able to say, okay, in order to get more compressed, I might to get a better quality of the camera of the picture, I might want to have more bits per pixel, and that's also changed. So all these kind of changes are in the end changes which data we are actually need to process into it. Okay, so what we want as data engineers or people or the guys in the end who kind of gets in the end the data and need to handle it. So we want different. We have several requirements, and this is what I want to show in this use case how we answer that requirements with this. The common functional patterns such as monad transformers and type classes. So first of all, we need a very easy way to reason that our code is fulfilling the specification that we are given with. So we get specification, usually is a big word sheet, and they have some table in it, and it's telling you how you can get each and every piece of information from the blob of byte arrays that you are getting from the logger. Okay, so we need to be able to very easily say, in order for us to be sure that we are not missing something between the specification that we got to the what we are doing actually in the in the data center. So we want that the code will be very easy to align to the specification. So this is one requirement which is important for us. And another requirement that is very much important, we have to understand when there is an error, and there's always are errors, because the different parties, as I said before, they might change. They might change things on the fly, and not every time this is coordinated. So there will always be some errors, and we are the ones who in the end kind of look in the data and say, guys, you need to fix here something doesn't play along together. Probably we should go back. So images, they are used a lot in the car, but when you see them visually in your eyes, they're very clearly, it's very easy to see that something went wrong on the road. Okay, and I think it's, not specifically to this piece of code, that any piece of code, we want to have it testable. So one of the main issue when you're working with this kind of input of byte arrays, so people tend to say, okay, I will put in my test, I'll copy a byte array that I know what is in it, and that's good enough from that. But that's not good enough for us. So the byte arrays might change, and we want our code that we can actually reason that, okay, this is testable, that this does exactly what it's supposed to do, not because there's some byte array that we know somebody took one day, and we want to actually have testable code. And this is, I hope I will manage to prove that we got that. So what will I show next? Because I kind of rushed it, so I'm maybe I'll have a look if there are questions. I'm not sure. I haven't looked. It doesn't seem like this. So what I will show next, because now I'll go more into to show code. So what I want to show is that we have managed to achieve a kind of a simple DSL to easily map the specification, as we said before. And I'll show, of course, a monad transformer. Yeah, finally, he's talking, this guy. And I will show a small enhancement for a monad transformer that kind of make our life easier for their requirement of understanding where error is coming from. And I'll show, example of why I love type classes is mainly also will show how the code is testable. So this is, and yeah, I'll show another cool car, I promise. Okay. From here, next. I will, yeah, okay. It's funny, I don't think I can actually achieve this raise of hands, but I want to, so I'll make my life easier and assume that everybody raise their hand when I say, okay, how many of you knows what is type classes? Thank you, everybody lift their hands. How many people know what is monads? Everybody lift their hands, and so on. I will try to explain at least my interpretation, because there is the official, but I'll show how my interpretation of those things to kind of to reference them in the code and show how they help to achieve what I wanted. So that's the last cool car. And let me go to a bit of code. So yeah, I haven't, for some reason, I don't see if there are questions and stuff like this. So I'll assume there's not. Where is Zoom?
There's one in the, if you click on the Q&A, I think there's one.
Yeah, but okay, that's probably the, when you're in presentation mode here. Okay.
Ah, yes, you have to exit it.
Yeah, okay, I don't know. Okay. Ah, here it is. There is. Okay, there is a question also. Even better. Does it means when I drive my BMW, all surrounding picture will be sent back to BMW data centers? So first of all, there is the question about consent, right? So whenever you give consent, only then data will be collected. And regarding images, I don't think that this is what is being collected. I mean, images are more sensitive and therefore they are not collected from the customers. So I hope this is answered this question. Okay, but there's no more other questions. So let me just go presentation mode and show. So the protocol that I'm going to talk about is MIPI. So it's a commonly used protocol for image transfer. So what basically this protocol is saying is, okay, I'll take the image, the frame, and I'll chunk it into different pieces, and then I can send these chunks over the wire, and you basically, there's a way to collect them and just collect them and rebuild from it the image itself. So what I want to show right now is I'll start. I usually like to start from tests, but this place was open. But I think here what I want to show first is how you can imagine. I cannot show, of course, the specification themselves. That's some of the things that I'm not allowed to show. But you can imagine yourself that just by looking at here, how easy it is to reference to some specification which coming. Okay, how do I take bytes out of something? So what do I need in order to get the chunk size? So yeah, it's pretty straightforward to see from it what exactly was the attempt. So I try to get the next unsigned, to get the length, etc., etc. In the chunks themselves, there are different type of chunks. So you'll see there's either metadata or the video chunks. So there are different chunks, but they're not very interesting for us. But again, you can see that I keep on using those chaining, those monadic chaining of getting the data, the information that I want out of my byte array or out of my T in this case. And what I do here is constructing basically the image that I want. So one of the ways that we basically do it is we have this kind of a chunk, and always I can do next on whatever payload you gave me. So payload might probably will be a byte array when I get it from the car, but it can be anything that I will know how to take bytes. I can get shorts, ints, longs, bytes, and byte arrays out of it. Okay, so byte arrays is to convert it from byte array to my T. So here you can see my first reference to type classes, right? So this is pretty clear. This is, I mean, what are from the signatures, what are the type classes that I'm going to show in a second. So is there any questions? Is the same question? It's the same question, okay. So let me go to byte extraction. So what I needed first, I need a way to kind of take whatever byte array that I got and to bring it into my representation of the payload. And what I want to achieve here, so I want to be without side effects, right? Because I mean, I think everybody in this call, I guess, though that side effects are bad, and it's, I mean, this, but working in the domain that we handle byte arrays and stuff like this. we tend, at least in my experience, we are tending to say, okay, I mean, even reading the bytes out of the byte array is not really an effect. But what we wanted to do here is to basically reason about it and also say, yeah, that's just getting the bytes out of the byte arrays and then being able to incrementally, so it's a very easy incrementally sequential algorithm to go, okay, get the first byte, unsigned byte out of unsigned int out of the bytes, and then get the next, the next, the next, the next. But it's very easy sequential algorithm, but it's also stateful, right? Because my byte is array is always, I'm kind of changing it, what is in it, or where I am in it. So first I'll scroll through the type classes. I don't think there is, it's pretty easy to reason about it. So what does it mean? I'll have a T, just teach me how you want to get byte arrays, how you want to get the bytes out of it. So give me the number of bytes, I'll give you the array with those bytes. And you can see the implementation that we are left in the end right now is basically the byte buffers, pretty commonly used. Same goes for the next, you'll see get bytes and unsigned, so all of them have their equivalent for signed and unsigned. I'll scroll to the more interesting part, and that will be my state monad. So again, that's pretty straightforward, but here we are. So what state state monad, I'll maybe give a short explanation what state monad says. So state monad basically want to say, I have some state and you can do some operation that return the value for it, and I'll return you the next state, right? So it's kind of a state machine, but is abstract away what is happening on inside. So you could basically change those, chain those operation, and always have the state carry kind of the state with you. This state monad. On the other hand, as we said before, I might fail to do that. So if the byte array are corrupted and they are not as I expect them to be, then I'll fail. There's a good chance that I'll fail. And this is why we won't try. So what monad transformers are basically coming to do is are enabling us to kind of combine these two monads. So there's so the behavior that the monad transformer, I always try to, when I try to explain it, is okay, what is the combination here, right? So my combination here, I'll have some state, I'll try to do some operation, but if I fail to do this operation, don't try to do any more states changes, right? So that's the normal explanation about the monadic behavior of try is you have this success route and the fail route. So the moment you're in the fail route, just don't do anything. We are on the fail route. There's no way back. Just short circuit it and let's finish with it. And state give me this ability to kind of say, okay, I keep on taking those bytes or the different bits out of this byte array. Okay. So. I'm using here a cat, so I know I've seen ZIO and cats. There's in the community some disagreement. I'm not a big fan of either. I mean, I don't have preferences here. We choose to use cats, so yeah, don't judge me for it. So the only thing which I want to maybe spend a bit more time on it, that one of the things that we really wanted to do is to be able to add this kind of information, what actually failed. So we need to know when I had, if we go back to chunk, so you can see that I said, okay, I want to take lengths and chunks, chunk type and subtype. But if I will just get these bytes out of the array, byte array, and I'll have a failure, if it's, I'll get probably a failure of index out of bound or some kind of cryptic that won't give me really information what and where did I fail. And therefore, what we try to achieve here is to basically to be able to add some hint for the attempt itself. So I can basically tell, I think it was more clear in the, here I can say, okay, if I fail, what I'm trying to do here, I'm trying to get out of the chunk the length. If there's any failure, I just, this is the hint that I want to add to this exception, whatever it is. Yeah, so how I achieve it here is basically by simply recovering. So whatever the try happened, so if you failed or anything, if you had a failure with this try to do this action that you, or the attempt to the action on this state, just add the failure with a hint. Okay, so I'll just, again, also the hint itself is you are free to do whatever hinting you want to do with it. Okay, so this is the enhancement part that I was talking about. Next one I want to show, what I would like to show is basically how we kind of created this DSL. So basically, how do we get this DSL that you can construct this chaining of transformations or state changes in a pretty in a for comprehension. So what we have here is again, I'm kind of abstracting from whoever you write the code, whoever, so maybe I forgot to mention it, but whoever gonna later on use this to write correlate the code itself to the specification is probably not gonna be the same guy who wrote it. So I'm trying to avoid and sit and decipher specification. Is not my favorite things to do. So I prefer to write a code that I can give to people which this is their specialty to understand the specification, and they can just easily change the code to fit to it. So what basically I did here, I basically enable, so I use again the beauty of type classes in combination with my state monad, or my state t try, and I just basically already encapsulate in it all whatever. So just give me what hint you want. I will give you I will give you the exception that whatever it's happened here, but I'll hint it with my own with whatever you told me it's necessary. So therefore, I managed to kind of enhance the try by giving the user the ability to hint what he actually failed on, well, what he was trying to do. Okay, so I think that I'm pretty. One thing that I wanted additionally to show is we talked about testable, right? And as I said before, yeah, so as I said before, one of the things that I really don't like is tests that I don't understand the inputs and outputs. So what was the input for this test? So if we will go to our, yeah, okay, sorry. Okay, so don't cooperate with me. Yep. So what I want to show here is basically that I'm able to also create images which are not byte arrays. So I can where are they? Where are they? Sorry. So I can generate random video chunks, and what I want to show. Come on. Okay, I'll just stick with this. So whatever I can show here is basically I can describe my images exactly what I want them to do, but because I'm using type classes in the end, I don't need to have any byte arrays here. So you won't see anywhere in my test that I'm using byte arrays. So, and here it is. So yeah, sorry for that. So you could see in the specification, if you remember in what I showed before in the code that kind of tried to align to the specification, if you remember, there was length and chunk type and subtype and so on and so on and so on. So here you can see I'm explicitly describing what my chunk's going to look like. and then I'm able to kind of say, okay, what is my mocked byte buffer, or what is my mocked payload, is basically just an array of those uints and uint16. So all these types that I'm going to actually extract with the specification. So I can easily define how my byte arrays would look like if I'll do always next by just really, here I'm really going stateful already, right? Because you have an array, and I'm going to always, when you say next, I'm going to give you actually the next in the array itself. So that's the beauty of at least in my opinion, the beauty of using type classes also on those on your input itself. So I'm able to kind of abstract away how I will get the different types of data out of the out of my input. Yeah, then tests are usually pretty easy to refer. Yeah, I always can see what the stats video looks like, and so yeah, you can see that it's pretty easy to look at it. So I think from my side, I pretty much said all what I wanted. I know it was pretty fast. I hope I didn't, I wasn't too fast on some points, but please feel free for any questions.
Thank you so much, Noam. If anybody's got any questions, feel free to ask in the Q&A section. But no, amazing talk. Thank you so much. Cool.
Yeah.
Have you, and questions been answered, hasn't it? Amazing. Well, thank you so much. Thank you so much, everybody who joined today. And thank you to both our speakers, Adam and Noam. Obviously, as usual, the videos will be posted very soon. So thank you so much, guys. Thank you. Thanks, Adam. Thanks, Noam.
Thank you.
Thanks. Have a good evening.
Oh, 1 second before you go.
Yeah.
Oh, sorry, Noam, there's one quick question there.
Yeah.
Have you tried Frameless?
Have I tried Frameless? Yes, I tried Frameless. We use it in some cases, but Frameless, the main problem that is with, I mean, it's not a problem, but it's used data sets underneath, and we use a lot of data frames. So that's pretty much, in some cases, it can be contradicting. Yeah.
Cool, and there's one more question there as well. Can you see the question box? I'm the beginner in FP. Can you please talk of difference between Kesley and monad transformers?
I mean, as I said before, I'm also don't see myself as a function developer savvy, but so I honestly I don't want to say too much, because I don't want to say an answer which probably somebody here will know better to answer. But again, my gut feeling is that Khaleesi is a bit more abstract than monad transformers. So monad transformers are pretty clear on what is there. They were pretty much straightforward, but Khaleesi is a bit more abstract.
Amazing. Thank you so much. Great. Thank you so much, everybody, for tuning in. Thank you again, Noam and Adam, for your talks.
Thank you.
Thank you, guys. We'll see you all soon.